Okay, so good afternoon, everyone. My name is Eric Cancès. I work at École des Ponts and INRIA Paris, and I'm going to talk about constraint optimization and give you a geometrical viewpoint. So let me start with some motivation. So as you know, constraint optimization is everywhere in quantum chemistry. Okay, so constraint optimization is everywhere in QC, quantum chemistry. So a few examples. So the first one is variational characterization of the ground state. So as Hassan told us, so the ground state energy is obtained by minimizing the energy of some wave function. Psi lives in some Hilbert space. In fact, in the, well, okay, anyway, in some Hilbert space. And the norm of psi is equal to 1. Okay, so that's the variational characterization. Of the ground state. So that's the first examples. Other examples are Hartree-Fock and Concham problems. When I discretize this problem for instance, in an atomic orbital basis set, we obtain two formulations of this problem. The first one is called the molecular orbital formulation of the problem. It consists of minimizing some energy functional, which depends on the matrix C. And C is the matrix of the molecular orbitals in the atomic orbital basis set. So it's a rectangular matrix, and which satisfies some constraints, which is C transpose SC is equal to identity of N. So here, N is a number of electrons or electron pairs, doesn't matter. Then here I have the overlap matrix. The overlap matrix is a square matrix of size NB times NB, and which is symmetric. Okay, and this is Hartree-Fock or Concham energy functional. In the basis set. Okay, and this is a constraint optimization problem, in fact, an equality constraint optimization problem, because I don't minimize the function E over a linear space or a vector space, but on a set which is defined by some equality constraints. Okay, so this is a molecular orbital formulation of Hartree-Fock or Concham. Mathematically, these two problems look very similar. And I can also write a density matrix formulation of Hartree-Fock or Concham. And this is this problem is as follows. So I have a different energy functional, which depends now on the density matrix. And the density matrix is a square matrix of size NB times NB, which is symmetric and which satisfies the constraints. Okay, so D SD equal D, and the constraint trace of SD equal N. Okay, and the relation between this functional E and the functional curly E is simply that E of C is curly E of C transpose. Okay? And this formulation is called the density matrix formulation of Hartree-Fock or Concham. Good. So this is the case for Hartree-Fock and Concham, but we also we could also formulate other variational methods such as MCSCF. Cancès, DMRG, all that give rise to constraint optimization methods. Gives rise to equality constraints optimization methods, optimization problems. Okay, so that's one point, the first motivation. The second one is that the geometrical viewpoint I'm going to explain here is also useful for time-dependent problems. Time-dependent problems. So, for instance, time-dependent DFT, time-dependent Hartree-Fock, time-dependent MCSCF, time-dependent Hartree, whatever, okay? And we have experts in the room, and this is based on the Dirac-Frankel principle. And the third argument is that more broadly, the geometrical viewpoint is useful to just to understand quantum mechanics. Let's say to better understand quantum mechanics. If you want to answer some questions are, for instance, why are there conserved quantities? What is spin? Okay, all that to really understand what spin is, you have to study the theory of Lie groups. And with the Noether theorem, you will see that the theory of Lie groups gives you the existence of conserved quantities. Explain why there is a spin variable. What is an elementary particle? And so on. And also, there are other kind of geometrical objects, which are called fiber bundles. And which are useful to understand, for instance, the concept of Berry phase. Some of you know. To understand also the Born-Oppenheimer approximation. Or what is a topological insulator? Topological phases of matter. And so on, okay? And all that is based on a geometrical description of the physical reality, okay? Good, so that's for the motivation. I think it's enough. And now Let's start with introduction. And to start very smoothly, so introduction. And to start very smoothly, I will start by recalling some basic facts about unconstrained optimization. Unconstrained optimization. So unconstrained minimization means that I'm minimizing some function over a linear space, okay, vector space. And let's start with 1D. So let f from R to R differentiable. And what you all know is that the set of minimizers of f is contained in the set that I call C of the critical point of f. So what's that? That's the set of x in R such that the derivative of f at point x is equal to 0. Okay, this set is called the set of critical points of f. Okay, so let me make a picture. Yeah, some function like that. Okay, for instance. And here you can see that I have several critical points where the derivative vanishes. So this one, this one, this one, this one, that one, and that one. Okay? So this is a set of critical points. Among these critical points, there are points which are not minimizers. So this one, for instance, is a local maximizer. This one is an inflection point, which is neither a maximizer nor a minimizer. Okay, but what is for sure is that the set of minimizer is included in the set of critical points. Okay, and what we would like to do first is to extend this very simple picture to equality constraint optimization problems. Okay, good. Okay, so let's do that. So let me first recall the extension to that to a function f. So if you take a function f from Rn to R, so in this case, the set of minimizers of f is included in the set C. So I just have to replace the derivative with the usual Euclidean gradient. So the set of x in Rn such that the gradient of x of f at x is equal to 0. Okay, and we just recall that the gradient of f is the vector composed of the first order derivatives with respect to each variables. Okay, so this is called the Euclidean gradient. Because we see later that there are other ways to define gradients, and this will be very useful in practice. You will see that later. Okay, so yes? Is there a difference between critical point and stationary point? No, it's a matter of, yeah. Yes?
I don't know if you will talk about that later, but if you don't have differentiable functions,
Yeah.
all that doesn't work. Will you?
No, I won't talk about that. It's completely different field. Non-smooth optimization is completely different field. So here I will focus on smooth optimizations because for Artifog, Concham, MCSCF, and so on, we are dealing with, well, MCSCF not quite, but almost. But for Artifog and Concham, we are dealing with smooth optimization problems. Okay. And we stick to that because for the sake of time. Okay.
Just in few words, what would change if you?
Well, a lot of things, in fact, because instead of gradient, you have to, if you have, so a classical case is when you are dealing with convex functions, so convex non-smooth optimization. In this case, you have to replace the gradient by the subgradient. It is also very useful in some cases in quantum chemistry. But again, I don't want to go into that because it's really, it's a huge field and completely different.
So Cancès, sometimes you have jumps.
Absolutely,
Okay.
absolutely. But we can talk offline about that. I will be happy to. But yeah, for the moment, let me. Yeah.
In boundaries, if you arrive, you have a minimum which appears on the boundary of the.
Yes. Okay. That's also something I will not cover. But yes, I agree. If instead of R, I'm minimizing a function on a closed interval AB. Then I if the minimizer is attained at A or B, then what I'm telling you is not true. But I'm optimizing on. In fact, as soon as here you have an open set, I will define what is an open set. Then this is okay. If you have the minimizing set is not closed, is not open, then it's not longer true. Yes. In constraint optimization, I want, well, for instance, I will cover fully Artifog and Concham, okay? And for these problems, you will see that in Artifog and Concham, there are no boundaries, basically, because we'll see that later. Okay. All right, any other questions? No? So far, so good? Okay. So let's now turn to constraint optimization. So as I said, constraint optimization is everywhere in quantum chemistry, but also in physics, in rational mechanics, everywhere. And so is in any 1, 2. Thank you, Andrea. I'm going too fast. I see. Okay. And as I say, as it is everywhere, in every textbooks of physics or chemistry, you have a section or at least an appendix recalling what you should do when you have constraint optimization. Okay. And I will name this section the Lagrangian trick, because it really looks like a trick. So what's that? So let me take the same notation as in the QChem manual, just to stay to quantum chemistry. So it's section A5 in this manual. Okay. So it's really there. I'm not cheating. So you take F from Rn to R. You take G from Rn to Rm. And you want to solve, to minimize F over the set of points in Rn, which satisfies the constraint G of x equals 0. Okay? So 0 here is a vector, okay, because this function here has m components. So G of x is in fact G1 of x. And it's a vector of size m, Gm of x. Okay. You assume that these two functions, for instance, are continuously differentiable, but I'm not sure it specifies there, but okay. And then what you do is that you introduce the Lagrangian. And the Lagrangian is a function of two variables, so x and lambda. So x lives in Rn, lambda lives in Rm. It's a real value function. And this function is defined as f of x minus lambda dot g of x. Okay, and so if I expand, this is the inner product in Rm. And so if I expand, I find f of x minus the sum of lambda I gi of x. Okay? And then the Lagrangian tree tells you that the set of minimizers of my problem 1 here is included in the set of critical point, or stationary point if you prefer, critical points of the Lagrangian. So what does that mean? It means that to find the minimizers of 1, so of f over the set of x such that g of x equals 0, solve the following problem. The unknown now is not just x, but x and lambda. So seek a pair, lambda, x and lambda, such that the gradient with respect to the variable x of L evaluated at x lambda is equal to 0, and gradient with respect to the variable lambda at L equals 0. Okay? And so we can easily write that. So this condition is what? So let me start with this one. So this one is simply the gradient with respect to lambda. When I take the derivative or the gradient of this function with respect to lambda, I find g of x. Okay. So this function, this constraint, this criterion is equivalent to ensuring that x is on the minimization set. And what about this one? This one is equivalent to the gradient of f of x minus the sum of lambda I gradient of gi at x is equal to 0. Okay? And observe that now this is a problem with n plus m scalar equations with m plus m scalar variables. Okay, so I have enlarged my problem. I started from a problem with n variables. Now I have a problem with n plus n variables. Okay, system of n plus m scalar equations with, oops, I lost the microphone. With n plus m scalar unknowns or variables unknowns. All right. Okay, good. But this really looks like a trick, okay? Because why? Okay. So here you really understand what's going on. Okay, it's obvious that if you know what is the derivative, okay, no problem. Okay, you are very comfortable with that. You are probably also comfortable with this one. Okay, but this, huh? Not clear what it means. Okay, Yeah, clear. Okay. So let's try to understand what's the meaning of this problem, of this. But first, before we go to that, let's give an example, okay, or maybe two. Okay, let's start with a simple example. Oops, sorry. Let's start with an example. So let's do something very simple. What did I take as a simple example? Okay. N equals 3, M equal 1, f of x equal x1, g of x equal x squared minus 1. Okay? And I don't try to interpret that, just, okay, I have a f and g, and I'll go, okay? So what is the Lagrangian? The Lagrangian is a function from R3 to R, and which associate to x and lambda. Okay, so L of x lambda, and this is x1 minus lambda x squared minus 1. Okay, fine. So let me write down the criticality conditions for L. So I have to seek x lambda in R3 times R such that, okay, the second constraint, so the second set of equations is just that. Okay, so this one easy. Just that the norm, that's the Euclidean norm of x is equal to 1. Okay. So what about this one? It's a gradient of L with respect to x1. So this is the vector E1. Okay. So I have E1. So E1 is a vector 1, 0, 0. That's the canonical basis of R3. And when I differentiate that with respect to x, I find minus 2 lambda x. Okay. Yeah. Because the gradient of f is the gradient of g, sorry, is I differentiate that and I find 2x1, 2x2, 2x3, and this is just 2x. Okay. There is a norm somewhere. Well, this is a norm. Well, this is my notation for the norm. Maybe I should. Okay, let's do that. Usually in math, when you work in RD, you just put that to. Okay, but I can put it. It doesn't matter. Okay. Yeah, that's a clear norm. Okay. So let's try to solve this equation. So what does it tell me? It tells me that x is collinear to E1, and that x has to be of norm 1. And so I found two solutions. I found a solution which is x equal, so E1. And the second one is x equal minus E1. The lambda corresponding to this one is 1/2. No, yes. And this one is minus 1/2. Right? Okay, so what are you doing? In fact, so this is what? The set of G such that G of x is 0 is simply the unit sphere. Okay, that's the unit sphere. And you are minimizing the first coordinate over the unit sphere. Okay, so what do you get? you minimize this coordinate over the unit sphere. And so what you get here, so I'm very bad at drawing, but okay, something like that. So you find this point, which is E1, and this one is E2. So this one is a maximizer, in fact, and this one is a minimizer. Okay? So this one is a maximizer of F over the set of over G minus 1 of 0. And this is a minimizer of F over the minimization set, which is G minus 1 of 0. Okay? So far, so good. And on top of that, we have a kind of geometrical interpretation of the two solutions that you get. Okay? So again, if you solve this problem, you won't find only the minimizers, but you will find several points, and among them, there are the minimizers. Okay? Oh, it's fantastic. Okay, so we should, I'm almost done then. Okay, but just to be on the safe side, let's do a second example, because if it works for two examples, it's fine. Yeah, okay.
Interpretation for lambda.
Yeah, okay, this will come later, in fact. Yeah, talk about that. Yes. Very good. But before that, let's do a second example. Okay, let's be, I'm a bit tight, so let's do things, let's do recycle this example. And I just do that, okay? Just to, I recycle the example. Okay, good. Well, okay, so then, blah, blah, blah. And what you get is you have to seek X lambda in R3 times R such that. So this equation basically doesn't change because the gradient of this function and the gradient of this function are the same. Okay, great. So I have E1 minus 2 lambda x equals 0. And the second equation is x squared equals 0. Okay. Okay. Yeah, I'm in trouble, right? Because there are no solutions. Because if this is true, x equals 0, and if it's x equals 0, E1 equals 0, but E1 is this vector. So the problem, okay? No solution. But maybe it's still okay. Maybe it's just because the minimization problem has no solution. Okay? But the minimization problem consists in minimizing the function f over the set of x such that g of x equal 0. But I mean, I have someone in this set. Okay? So the set of x such that g of x equals 0 is not empty, just 0. And so the minimizer of f on this set is just 0 because there is only this guy in the set minimization set. Okay? And so yet 1 as a minimizer, which is 0. Okay? So the conclusion is that, unfortunately, the Lagrangian trick does not work all the times. Okay?
Did they talk about this in QChem?
No, 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 no. When it doesn't work, it's better to. Yeah. No, no, but in it's okay. To really understand. Well, okay, you will see. Okay. What is lacking is an assumption on G, and I will tell you what is one possible assumption on G for which you are sure it's going to work. Okay, so we have to address two issues. So the purpose of this lecture, well, it's a partial purpose of this. Let's say first goal of this lecture. First goal of this lecture. Give assumptions, give, let's say, sufficient assumptions on F and G for the Lagrangian trick. Work. And in fact, we will apply this to the Hartree-Fock and Kohn-Sham problem in the molecular orbital formulation. And the second is to find a setting in which the Lagrangian problem is minimal. And I would say no redundancy. Or it's equivalent to take the smallest possible M. Okay, because sometimes the set like that, there are several ways to define this set. Okay, we'll try to identify a minimal one. Yes. Yeah. Yeah.
Suppose we put GX equal epsilon and
Then it's okay.
and then we make tended to.
Yeah. So then what?
Allowed?
It's allowed in the sense that, but lambda will go to plus infinity. Okay. Yeah, yes, but in the limit, lambda goes to infinity. And yeah, but this is a very basic example. We can cook up more. Yeah. Yeah. Okay, so any questions so far? Okay. Yeah. Okay, thank you. In fact, so I define my minimization set as the set of X such that G of X equals 0. But assume that, for instance, you have a G of X, which is G1 of X, and then G2 is just 2D1 of X. Okay. Then obviously you don't need the second condition because the set G of X equals 0 is just G1 of X equals 0. Okay. So the G is too large. And if it is too large, you will have you have a redundant Lagrangian variables, and the problem is bigger than it should, and so it's more difficult to solve numerically. Okay, so the goal is to identify the smallest M for which you can apply the theory. And we will see, for instance, a good example is Hartree-Fock and Kohn-Sham in the density matrix formulation. Okay, in the density matrix formulation. In the density matrix formulation, I minimize over the set of D such that D square equals D, trace of D equals N. Okay, assuming S, the overlap matrix is the identity. So I could say, okay, let me define G1 of X equals this, G2 of X equals this. Okay, I have a large number of constraints. And in fact, the number of constraints that you have is much too big. Okay, we'll see that in detail later. Okay, and so in this case, it's a very bad idea to say, okay, G of X, G of D will be first the matrix and second this condition. Okay, that's a very bad idea. Okay, and so we'll show what we should do in this case. Okay, it's a bad idea because you have too many variables. Okay. So to proceed, I need to introduce some tools from differential calculus. Well, basics of the differential calculus. Okay. And so to deal with all the cases I'm interested in just one setting, I have to introduce the concept of Euclidean space. So I take V, an Euclidean space. An Euclidean space is a finite dimensional vector space endowed with an inner product usually written like that. Or I don't use that. And associated norm and the norm associated with the inner product is simply that X is the square root of the inner product of X and with itself. And there are many Euclidean spaces used in quantum chemistry. So useful examples for quantum chemistry. So the first one is Rn, of course, so R to the n with the Euclidean inner product. So this one, you all know it. It's, let's say, XX prime. XX prime is X transpose X prime, or if you prefer, the sum of xi prime. Okay. Another useful example is Rn, but this time endowed by the inner product S, where S is the overlap matrix. Okay. So in this case, it's X transpose S X prime, and S has to, and there is a S prime missing, and this is the overlap matrix. And this matrix has to be symmetric. And it also has to be positive definite, which is the case for any overlap matrix if you have non-redundant basis set. Okay. Okay. Then I also have the case of matrix spaces. The third example is V equal R n times n, endowed, and the inner product, and the Frobenius inner product. Okay. And this inner product, it is defined by, so I have two matrices. And this is a trace of M transpose M prime. Okay, you can check that it is an inner product. Okay, it's called the Frobenius inner product. And lastly, you can take N times N symmetric, and also with the Frobenius inner product. And in this case, MM prime is also the same guy, okay? But the thing is that as M is symmetric, this is also MM prime, trace of MM prime. That's a detail. Okay? And this is enough to cover basically all the, well, at least the Hartree-Fock and Concham cases, but also Cancès CF and so on, okay? DMRG. Good. So do I need to recall what is an open subset of Euclidean space? So who knows what is an open subset? Okay, so not everyone. So let me explain it. It's 2 minutes, so it's worth it. So open subset. So a subset omega in V is called open if the open ball in V of center of, sorry, if for all x in omega, there exists some epsilon positive such that the open ball in V with center x and radius epsilon, that is the set of point x prime in V such that the norm of x to minus x prime, that is the distance from x to x prime is lower than epsilon, is included in omega. Okay? And this is called the open ball of V with center x and radius epsilon. So what's the point in defining open sets? It's to avoid the kind of issues Andreas mentioned. In fact, if you have a point in an open set, you take, so X is a point in an open set omega, okay? It means that there is a small ball, okay, with of center X and radius epsilon, which is completely contained in omega, okay? And the good point is that if I have an open set, I can take any X in the set, I can move in any direction from X, okay? That's the point, okay? We can move in any direction. And so I will be able to look around and move in any direction, okay? And this is important if I want to find optimality conditions, okay? Because if I cannot move in a given direction, this will constrain my optimality condition, okay? For instance, if you take, so for instance, the set AB is open. Or let's say 0, 1, okay. 0, 1 is open in R. Well, so this is a French notation, okay? This is a French notation. This is English, everywhere else, I guess. This is open in R, and this one is closed in R, and it's not open. Well, no, sorry, I shouldn't write that. Okay, not open, say. Okay, right. And the point is, so this is not open because if you are at 0, Okay, you can move in the positive direction. You cannot move in the negative direction. Okay, and so therefore, if I have a function, for instance, so I minimize the function on 0, 1, and if this function is like that, okay, and the minimizer is here, and at this point the derivative is not 0. Why? Because I would like to minimize f by going this direction, but I'm not allowed to because I'm sticking to this interval. Okay, and so to have nice, let's say, nice optimality condition, or let's say simple optimality condition, because it's of course possible to address the case of a closed subset. But for open, if I want to have a simple criticality or optimality conditions, it's good to work in open subset. Yes.
What constraint, the equality constraint may allow you to define a closed set, right? But right before you had the
yeah, that's right. It's a very good question. But we will see that in fact it's closed in the ambient space, but it's open as a manifold.
Okay, yeah.
Yeah, we'll see that later.
So
yeah, but I mean, but you have to put the right topology on it, yeah, and the right differential calculus on it. Yeah.
In connection with this comment, so because we were talking about minimizers before, so
Yeah.
if I look at the critical points, once I have the true free variables, I mean the n minus m.
Yeah.
So the critical points you get from
The n minus m.
No, I mean you have m constraints.
Yes.
So you could identify n minus m.
Yes.
Variables.
Variables. Okay. Independent variables.
So you
Okay.
were talking about minimizers, but if you look at the critical points,
Yes.
those are supposed to be exactly the same as the ones from the Lagrangian or not?
The Lagrangian is a function in a much larger space.
Yes.
Okay, so it's but
you may
yeah,
find-
what is under some assumptions, the critical points on the function on the minimization set, the manifold, will be the critical point. Well, will be such that there exists some lambda, such that x lambda is a critical point of the Lagrangian. Okay, but we need assumptions, in particular on G, for that. Otherwise, it's not true, as we saw. Okay. Okay. So then I have to talk about derivatives. So let VW be Euclidean spaces. And omega, an open subset okay, so let F from omega to W and X in V. So F is differentiable at X if I take, if there exists some map from V to W, which is linear, very important, such that for H in V, H small, F of X plus H, so I take a small variation around X, okay, I go there, for instance, is of the form F of X plus some linear part, which is df of X applied to H, plus something which is small compared to the norm of H. And we denote that by little o of H. Okay, some example. If V equal Rn and W equal Rm. So dfx, so it's linear from Rn to Rm, and a linear map from Rn to Rn, M, can be represented by a matrix, okay? Donc, is identified with what is called the Jacobian matrix. And that's the matrix of the derivatives of the components of f. So let's assume that f is these are the components of f, and the Hessian matrix is simply the matrix of the derivative of the components of f with respect to the variables x1, xn. So, and it's in this order. 1 xn dfm dx1 dfm dxn. And it is of size r, so the number of rows is m, and the number of columns is n. Okay, because you want to apply this matrix to a vector in V, okay, and end up with something in W or Rm. Okay, so this is what you should do. Okay, so that's the example one with in Rn. So now let's consider an example in a matrix space with a Frobenius inner product. Example 2. So I take V equal R. So let's do quantum chemistry. So I have a space of orbitals, okay? Size of the basis, number of electrons or electron pairs, and F and G, W equal R n times n symmetric, and G from V to W, which associate to some matrix C, G of C, which is C transpose SC minus identity, where S is, as before, the overlap matrix. Okay? So this is a function which will be useful to me because that's the function which defines the set of molecular orbitals. Okay? Because set of admissible molecular orbital matrices, that's the set of matrices of size nb times n, such that C transpose SC equal identity. Okay, that's what you have in the Hartree-Fock or Concham formulation in the molecular orbital setting. Okay, and so this is just C in the space V such that G of V equals 0. Okay, so this is why this function V is useful. Okay, it naturally pops up in quantum chemistry. Yes. What? G of C. Yes, thank you. Thank you. Okay.
There are matrices of size and then n, right?
Yeah, and B, yes, n times n, symmetric, yes, and symmetry, very important. Okay. It's also true without the symmetry, but if I put symmetry, G, yeah, is smaller, and so I gain. We'll see that it's very important for. We'll see that it is important to restrict the space W to symmetric matrices. Okay. Yes. But because I haven't, I'm going to do it. Do you want to go? You want to? Okay. No, no, absolutely not. I'm going to compute the derivative, but give me 2 minutes. Okay. So how to compute derivatives in this case? Okay. So here is I don't want to do that. Okay. I don't want to. It will be a mess. Okay. If I reshuffle this matrix in a big vector. Here it's symmetric, so which coefficient should I choose? Okay, it's possible, but it will be a mess. Okay, so instead of that, let's be more clever and use this definition. Okay, so what should I do? I take some C and some variation of C. Let me call it, I don't know, delta C. Yeah, okay, I don't like so much. Well, Antoine would be very happy, but. Okay. What? H is more Hamiltonian. Okay. Well, capital X. No. Okay. Okay. Allez, I go with delta C, but it's really okay. Okay. Delta C. Okay. Good. But it's not, I mean, it doesn't need to be small. Okay. It's something. That's why I don't like so much delta C. Okay. Because, well, okay, it's small. Okay. It's not infinitesimal. It's small. It's not infinitesimal. It's small. Okay. Good. So let's do it. So what's that? So it's a C plus delta C transpose S C plus delta C minus identity. Okay, I expand that using the bilinearity. C transpose SC minus identity is G of C. And then I have plus terms which are linear in delta C. And plus a term which is this one. And this one is small, okay, because it's delta C square, okay? So it's a little o of delta C. And this one is linear in delta C. Okay? And so I have identified my derivative. dg of C applied to some delta C is a matrix delta C transpose SC plus C transpose S delta C, right? Okay, so that's the derivative. So now let's talk about gradients. So to define the gradient, I need to a function from V to R. So we already see what is a gradient in the case where V equal Rn and the inner product is a Euclidean inner product. Okay, it's the vector of the first derivative at x. Okay, so this one not interesting. But let me recall it just in case. So V equal Rn and Euclidean inner product. No, let me first define the gradient in the general case. Assume that it is differentiable at x. The gradient of f at X is a vector, is a unique vector denoted like that, which is a vector in V, such that for all y in x, delta x, okay, I continue with the copy notation, okay, delta x in V, dfx of delta c is gradient f of x delta x. So why is it unique? Why does it exist? What is it? Why is it unique? It's a consequence of Riesz theorem for those who know it. Otherwise, you just count the dimensions because we are in finite dimensions. But so it's going to work. But trust me, there is a unique vector in V for which this is satisfied. Okay. So examples again. So the first one is V equal Rn and the Euclidean inner product. Well, what you know is that df of x. So in this case, df of x, it's applied to delta x is the sum for I equal 1 to n of the derivative of f, that's just a Taylor formula, delta xi. Okay. Because it's what I get in Taylor formula. Okay. You want me to do the details? Or? What? This is a vector, and this is the I component of the vector. Yeah. This one does not need to be small again. It's defined for all. Yeah. Okay. Okay. And so you can see that this is delta x with the one we had before. Okay. That's the usual case. But now let's modify the inner product. And you do that all the time in chemistry when you have an overlap matrix, which is not the identity. So V equal Rn, but then I change the inner product. It's the S inner product. So the derivative doesn't change. Why? Because if you go back to the definition of the derivative, it's here, okay? It's linear plus small. If I change, I'm in finite dimension. If I change the inner product, I change the norm, but I don't change it a lot in the sense that the two norms are always equivalent in finite dimension. And therefore, if it is small for some norm, it is small for all norms. Okay, and therefore, this just has to be linear and continuous, but in finite dimension, everything which is linear is continuous. And so the differential, the derivative doesn't change. Okay, so that's important. The derivative or the differential. Some people talk about derivative and other differential. Differential does not change. So df of x, it's still this one. But the gradient does. And how does it change? Let's come back to the definition. The definition, the generic definition is here. So what do I have? I have that for all delta x in Rn, I have that this has to be equal to the gradient. So just to specify that I'm using this inner product, okay, I will put an S here, just to say that I'm using this inner product. And by definition, this inner product is this vector S times delta X, right? And this is the usual Euclidean scalar product. So I will put it with identity, just to say that it is for S equal identity. Transpose delta X. Okay? And so if I identify the two formulae, I find that thus the gradient of f at point x for the S inner product is what? Is S minus 1, is that right? Times the usual Euclidean gradient. Yes. Yeah. I test the look. This is the definition of the gradient for a given inner product. Okay, for the inner product of V. Okay. I compute the gradient for the usual Euclidean scalar product, and then I find this vector, which is the usual one. Okay, and then I do it with this inner product, and I find this relation. And so now I also have this. And then I identify this is true for any delta x. And as this is true for any delta x, necessarily I have that. Okay?
So because usually what we do is that we rotate the bra and the kit by S minus half.
Sure, will be the same.
It will be the same.
In the end, yeah, but it's important to figure out what, because then I will give I should have done that before, but I'm going to give a geometrical interpretation of the gradient. What's the gradient, in fact? Okay. And lastly, what's the gradient and why is it an important object in optimization? And lastly, third example, V equal then a matrix space. And I will take f of C equal trace of HC, okay? C size transpose, sorry. Like, yeah, well, what you have, that's the first term in the Hartree-Fock function model, okay? So let's compute the derivative of it. So to compute the derivative, I compute f at C plus something, okay, small, but not that small, doesn't matter, okay? Not infinitesimal. And then I expand in delta C, and voila. And you can see, without too much trouble, that you will get this plus the trace of, so what do I have? I have HC delta C transpose plus trace of H delta C C transpose plus trace of H delta C transpose, and believe me, this is something small in delta C. Okay, and so the derivative is that. So maybe I can simplify this expression a little bit. Because I have some properties of the trace. The first property, yeah, I forgot to say that H is a symmetric matrix. Okay, it's a Hamiltonian matrix, and so it's a symmetric matrix. So what I was about to say is that this is, so the trace, so this one, I can put it here if I want, okay? Because of the cyclicity of the trace. No, I won't do that, in fact. What I will do is that I will transpose that. And then this one is fine. And this one, I will just put this one up there. So I'm allowed to do that because I have some important properties of the trace. So the first one is a trace of A transpose is a trace of A. It's obvious. The trace of AB is a trace of BA. So this property is called the cyclicity of the trace. It's used everywhere in quantum chemistry when you manipulate the expressions. Okay. And to go from here to here, I just used that this property, and to go from here to here, I used this one. And then I also use, I'm going to use that if you take AB transpose, it's B transpose A transpose. Okay, simple rules of linear algebra. And so I transpose that. I find trace of and also that A transpose transpose is equal to A. Okay, that's the, okay. If you don't know that, write it somewhere because that's very important, okay? So I applied the third rule here, and I find, so delta C transpose transpose delta C, then C transpose, then H. And this one is also trace of C transpose H delta C. Okay. Then you can see that I can put this one here using again the cyclicity of the trace. So this is twice the trace of C transpose H delta C. Okay, good. And now what is the gradient? So I equip this space with a Frobenius inner product. And by definition, the gradient of f at point C is the point such that for all C, the derivative of f at point C at delta C is equal to gradient f of C delta C for the Frobenius inner product. Okay. And what's that? Just the trace of f of c transpose delta c. Okay? And so it's very simple. I just have to identify these two expressions. Okay? You can see that this is also the twice, or let's say, trace of 2hc transpose delta c. Okay? And therefore, I identify this, and I find that the gradient of f at c is just 2hc. Okay? And hence, gradient f of c is 2hc. Okay? And so this derivation is, is very simple, in fact. When you are used to it, it's very systematic and very simple. What you just have to know is that, okay? So now I still have 10 minutes. See you, Alicia. Yeah, I don't know. Yes. Okay, yes, that's a good point. Okay, if you have, but if you have a function defined on, so you on a Hilbert space, so you need completeness. But if this is defined on a Hilbert space, and if the function is differentiable on a Hilbert space, then you can define its gradient. Yeah, so it's possible. Yes. Yeah. You need completeness. That's all. So you need a Hilbert space, not just.
Meaning that all norms are equivalent?
No, that's also something different. So so that's thank you for the question. It's a very good point. Okay, if you have a function f defined on a Hilbert space, so with a Hilbert space is a space with an inner product and an associated norm. If you fix the inner product and the norm, then you can talk about a differentiable function. And if the function is differentiable from, if a function from a Hilbert space to R or C, or let's say R is differentiable, you can define its gradient, okay? The thing is that if you take the same space in the set of elements, but put a different inner product, then you may have, the function may become non-differentiable, okay? It will stay differentiable if the two norms are equivalent. And if they are equivalent, then the derivative is the same for the two inner product, but the gradient will be different. Okay. Okay, so in 10 minutes, let me just explain why the gradient is useful. So geometrically, the gradient is the vector of E pointing toward the steepest ascent direction, whose norm is the steepness. I'm not sure this is an English word. Jack, is it? Yes. Okay. The steepness of the slope in this direction. So mathematically, it means that if the gradient of f at some point x is different from 0, then gradient f divided by the norm of grad f. So that's a unit vector, okay, which can point in any direction, will be the arcmax of df of x v for v in v with norm 1. Okay, so this is the variation, this is the first order variation of f in any direction. And then you consider a direction of norm 1, and you go all around, and you find the direction in which the first order variation is the largest. Okay, and this gives you the direction of the gradient. Okay, and then the norm of the gradient is the slope, so d over dt, of f of x when you go in this direction. So it's t gradient f of x divided by grad f of x at t equals 0. Okay? So here I don't need to be in Rn or in any space. Okay, it's completely general. It works also in a Hilbert space, infinite dimensional Hilbert space. Okay. Okay. And why is it useful? Extremely useful in optimization, because you know that if you go in the direction of the gradient, the value of the function will increase. So if you go in the opposite direction, it will decrease. And so to minimize, as your goal is to minimize some function, if you go in the direction opposite to the gradient, the function will decrease. Okay, this is why it is so important. Okay. If one goes from x a bit in the direction opposite to the gradient, the function, the value of f will decrease a bit. And this gives rise to the fixed point, no, a fixed step gradient algorithm. Steepest descent, yeah, which is also steepest descent. Algorithm. You are at, so it's an iterative algorithm. So you start from choose x naught, that's the initial guess in V, and some step t positive but small enough, and then iterate as follows. So you are in xk, and then you move a little bit by t in the direction opposite to the gradient. Okay. Geometrically, it's what you have. You are at xk. Well, I start from x naught. I compute gradient f of x naught. And then I move a little bit in the direction opposite to the gradient. I find next one. I compute the gradient at this point. Maybe I should put different colors just to be sure that. One, oops. This is green, up. Okay, and you find this point. Okay, and you will see with Antoine Levitt that if the function is nice and if t is small enough, then this algorithm actually converges globally to a local minimum of f, okay, on V, okay? So I think it's almost time to stop. So what we have seen is that it's very convenient in quantum chemistry, but in fact in any field to work when you have a minimization problem, to think of it as a minimization of a function. So first for unconstrained minimization in a Euclidean space. In an Euclidean space, you can define a gradient, okay? And if you follow the direction opposite to the gradient, you minimize, you decrease the value of the function. It's a way to minimize the function, okay? So this is an algorithm for flat spaces, for linear spaces. What we will see next time and is how to extend that to cases where you don't work on a flat space, but on a curved space. It's called a manifold, okay? Defined by a constraint g of x equals 0, okay? And then we'll apply that to Hartree-Fock and Concham, first in the molecular orbital formulation, and then in the density matrix formulation, okay? Then I think we will, okay. I'm not sure we'll be able to cover everything. I'm writing lecture notes. They're not ready yet, but hopefully they will be at the end of the week. And we'll, of course, share them with you. Okay, so thank you for your attention. See you tomorrow.